Small mistake, ma. Strict binary tree. Then comes the next one, that is skewed tree. Skewed binary tree. Under skewed, we are having two more types. That is left skewed and the other one is right skewed. Yes. Wait a second, I'll share it again. A small pop-up window box is coming now. To remove that, I've closed it. Now I started sharing it again. So first type of binary, first type of tree is binary tree. By the meaning itself, it is suggesting that by means two, binary tree. That means the tree should contain at least two children. At least two children, at most two children. It should contain only two children. At least, at most. Yes, at least two children, at most two children. The tree should contain, the tree should contain how many, ma? It should not go beyond two. Then I should write at least or at most?
At least. At least.
Ma, at most two children. At least ante kanisam rendu. At most ante kachitanga rendu. Difference was there. So at most two children. At most two children means either it can contain no child, that is 0 children, or it can 1, or it can 2. But beyond this, it should not go. That means every node in the tree must contain. Every node in the tree. Every node in the tree. Every node in the tree must contain at most two children. That means your parent root node. Suppose you have taken one root node as some A. It should have a child, some by the name B, followed with the name C. How many childs are there for the A? 2. This is an example for your binary tree. This is an example for your binary tree. Complete binary tree means it is also a binary tree, but it should complete the nodes from left to right, level by level. For example, in certain situation, I'll write it, ma. I'll open one paint window. Wait a second. I'll open whiteboard. Why all this? Yes, in this whiteboard, suppose a node was there. Root node is your A. For that A root node, two children are there by the name B and C. Now, I did not add the childs for the B. Now, I am adding one child for C, left child, D. Is it filled completely? Is the left child having childs? No. Such kind of a tree may be a binary tree, but it is not a complete binary tree. Complete binary tree means it should fill the childs from left to right, first criteria. Then the next criteria is level by level it should get filled. then only it is called as a complete binary tree. Then the another one is, what is the next type of the tree, ma? What is the next type of the tree? Full binary tree. There is a difference between the complete binary tree, sticked binary tree, full binary tree, ma. So next one is suppose there is a root node A. Sorry, I opted vanishing pen. Yes, ma'am. Suppose a root node was there. It is having a child. And even the B node is having left-right chains. Such kind of tree is known as your complete binary tree. And full binary tree also. Now I am going to tell the difference between the complete and full binary tree. This can be called as a complete binary tree and full binary tree. Please look at the difference between the complete binary tree and full binary tree. Suppose if I add a child for the left node, this might be called as a complete binary tree, but not the full binary tree. What is meant by full binary tree means each node in the tree must have either 0 child or 2 children. That is what the full binary tree. Complete binary tree means all the level by level it should keep on filling. That means if I don't have a child at E for B, left child was not there. Left child was not there. Only right child was there. Sorry, left child was there. No right child was there. So this particular situation is known as binary tree, but not it is a complete binary tree, nor it is a full binary tree. But it can be called as a strict binary tree. It is having either 1 child or 0 child or 2 children. So it comes under binary tree, but not complete or full. Are you getting my words? If you want to make a tree as a complete or full binary tree means keep on filling the childs from left to right. Level by level, it should get filled. Suppose if you want to make any binary tree as a full binary tree, you should have for each node at most 2 children. Such kind of tree is known as your full binary tree. Here are some examples for it. Now please at the next binary tree. That is skewed binary tree. That means the tree, skewed means what? It is bending towards one particular direction. Either it can be towards the left or right. So depending on the elements which you have inserted into the tree will be skewed either to the left or to the right. So please look at here. Say whiteboard. On the whiteboard, left skewed means A was there. For that, only the left child was there. No more right childs. In certain situation, it is called as a left skewed binary tree. No more right child, at least one will not be there. Right? What is this particular tree example is called? Left skewed binary tree. And there is a huge disadvantage by using this skewed tree. Half of the memory of the tree is not at all utilized. But the height of the tree is very heavy. Okay? Right. So this is what the left skewed ma. Now please look at the right skewed. The same representation will be there. That means no more left childs, only the right childs. Okay. These are the different types of your binary tree. Are you comfortable with this binary tree? And it always represent with a node representation of the data structure followed with the three parts, that is data part, left link part and right link part. Left link part indicates the left child address, right link part indicates the right child address. Are you able to follow this right skewed tree now? Yes, this is what about your types of trees of binary tree. And by taking this binary tree, one example I'll give you. Suppose I just want to create a tree with some elements. I'll take some elements. See, some 10, 20, 30, 40, 50, 60. These are the elements are there which you want to insert into the tree. Can you please tell me which element we have to insert first? So 10. Obviously, I'll be taking 10 as the first node. Then I just want to create its left child and right child. So how can I create it? Now to it, first I am taking it as a left child. So once I picked it, the left child is 20. Then after, I just want to take 30 towards its right child. Wait a second, I'll draw the line. Here is my node 30. Then now I just want to make here is your 40. 40 and 20 right, I am making it as right, I am making it as 50. Then 30 left, I am making it as a I'm making it as a 60. Yes. Are you able to see? Is it a binary tree? Every node is containing at most 2 children. Beyond 2, we don't have anything. Now, by looking at here, if I want to find 50 value, if I want to search 50 is present in the tree or not, what I have to do? I have to compare it with the root node. I have to compare it with the left child. I have to compare it with the right child. Then the left child, then the right child. In the fourth iteration of your search algorithm, you are getting that element is present in the tree. Is it an efficient way to find an element in the binary tree? Is it an efficient way? To overcome this search inefficiency, we have developed the next type of tree, that is binary search tree. Binary search tree. What is the definition of this binary search tree means? I'll share it. Wait a second. What is the meaning of this binary search tree means? It is a binary tree with some condition. What is that condition, my dear? Left less than, root less than, right. That means my left element is there, no? That should be less than the root. And my right element should be greater than the root. And don't write equal to. Trees duplicate values are not allowed to construct it. Unnecessary wastage of the memory to store the value. That's the reason we don't allow the duplicate values. We avoid them. Whenever we occur one element value, that once inserted into the tree, we won't repeat the iteration again back. Okay. So duplicate values are not allowed. Right. So binary search tree definition is what? It is a binary tree with one condition. What is that condition? Left less than, root less than right. Now, suppose if I want to construct a binary search tree with some elements 45, 67, 78, 34, 12, 10. These are the elements. So what will become the root? Yes, can anyone tell? First element will be the root node, right? 67, is it greater than 45 or less than 45? Greater than. So it will become the right child. So 67 will be your right child for 45. Now you got 78. 78 is what? Greater than 67. It will become the right child of your 67. Now we encountered 34. Is 34 less than 45 or not? Yes. So we'll add it as a left child. Then 12. Less than 45, less than 34. So make it as a left child. Yes, now what is the value? What is the value? Next value? 10. Less than 45, less than 34, less than 12. So it will be a left child for your 12. So obviously, what is your tree now? 45, 34, 67, 12, 78 and 10. What is the least child? 10. What is the root node? 45. What is the left child parent? 34. What is the right child parent? 67. This is what the construction of your binary search tree. And what are the operations we can perform upon any data structure? Insertion, deletion and display. So what are the different ways to display any tree? Means 3 different ways, ma. Actually, there are 7 different ways, but mostly we will be using only 3. Those are the popular ones. That is in order, pre-order and post-order. Okay. In the in order, we follow the principle like left, root, left, root, and then right. That means the root will be in between the left and right. That is the meaning of in order. In. And for binary search tree, in order will be always giving me the ascending order of your elements. Ascending order of your elements. In order will always give you the ascending order of the elements. So pre-order means first the root should come. So root followed with the left, then the right. I'm sorry. Yes. Next, the post order. Post order means the root should come last. So the procedure is left, right, then the root. These are the 3 different traverses which we will be using in our tree traversal. Now, by looking at the previous example which we have constructed by using the condition of binary search tree, can you please tell me what is the in order traversal and what is the post order traversal? Can anyone? Can anyone from the class? In order for this tree. In order means first I said the left. What is the leftmost element? 10. After 10, is it having a root? Yes, that is 12. Is it having any right? No. So skip it. Don't write it. Once you finish the leftmost node, what is the root? 34. So continue the process. Right was not there. To skip it, go to the root 45. Then did you finish all the left of it? Root is also finished. Then going back to the right. Under right, are you having any left chain? No. So please look at the root 67 followed with the right. For that right, are you having any left? No. So obviously we are writing 78. Now please look at the elements in the tree for the in order. Are you getting them in the ascending order or not? Did you find the result?
Yes.
Yes. Now please look at the pre-order. Pre-order means first my root I should display. What is the root? 45. Then I should visit the left. In the left I am having the root. So 34. In the left I am having the root. 12. Then the left. For that left, do I have a right? No. For that left, do I have a right? No. Then I am coming to the right. In that, root was there. So 67. I'm sorry, I should give a space. 67. Some space followed with the 78. Because no left, no, I am moving to the right. This is what the pre-order. Now please look at the post order. That means the root should come the last. First I am visiting the left. Do I have a right? No. So I'm moving to the root. No right, no? Then I'm going to the root. Left was finished. Do I have a right for 34? No. So I'm moving to the root. That is 34. Then, do I have a right for it? Yes, I do have a right. In that, do I have a left? No. So I have a right. So I'm printing it. That is 78. Followed with the root. That is 67. Overall, what is the root? 45. By taking this particular traversal example, we can consider a particular tree is a binary search tree or not. And one more point you need to remember that in order will always gives us the ascending order. And sometimes in the question they might be asking like, they'll be giving you the traversal. They are asking you to construct the tree. Or they might be giving the tree, asking you to construct the traversal. Vice versa will be asked as the questions, right? So either of the two combinations, if they give you, you need to construct the tree. This is what a brief description about your trees concept. Let us move in detail with the theory part about it. Okay. So this is what about a binary tree concepts completely. Please look at this. Notes in depth, ma. Now please look at the definition. I'm repeating it. Binary search tree means it is a binary tree followed with a condition that the list should be in an order that left less than the root less than the right. Here is some example, same which I have inserted just now. Did you understand with that example?
Yes.
Okay, ma'am. Here you go, the steps for it. One more example. If I take 43, the elements, look at the elements. I'll repeat it again. 43, 10, 79, 19, 12, 54, 11, 9 and 50. Here 43 is the root node because which is the first node that we need to take it as a root node. Then the next element is 10. It is less. I'm substituting it as a left child. 79 greater. I'm adding it as the right child. 90 greater than 79. So right child of your 79. Then 12 less. So I'm adding it as a 10 right child because it is greater than 10. Next element is 64. So it is greater than 43 but less than 74. Sorry, less than 79. Then the 11. This is what the final tree for that particular element. Right? Did you understand completely about binary search tree and its traversal? Can I continue with the AVL tree? AVL tree is very, very important, ma. We are having a huge... Yes, ma? First, let me know the disadvantage of this binary search tree first. Let me give the disadvantages first. Then I'll go why we have introduced with this AVL tree. What is the disadvantage of this binary search tree means? Suppose the elements are like this. Suppose the elements are like this. Suppose the elements are like 10, 10, 20, 30. Yes or no? If the elements are like this, how the tree will be? Is it a left skewed or a right skewed? Greater than. So I'll be adding it as a right child. Then 30. I'm adding it as a right child because according to my condition, it will become as a right child for me, right? So with my example, if I take the elements in any order, either I'll be getting the left skewed or right skewed. That means unnecessarily I'm wasting the half of the tree and I'm making the tree lengthy. So to overcome this, I should get into the concept like balancing of tree. So how can I balance the tree? Means by using the concept of Adelson, Willisky and Landis in the year 1962, they have introduced the concept to balance the tree by rotations. To balance the tree by rotations. What are those rotations? How it will be done? We'll see in detail with the example. Okay? Please look at the theory first. So, Adelson, Willisky and Lendy, these three people have adjusted the extra space which has been made while you are inserting the elements into the binary search tree. So, how it got balanced? That we are going to see here. And remember one thing, before checking the balance, we need to know what is balance factor. Balance factor means it is the height of the left subtree minus height of the right subtree. What is meant by balance factor? Height of the left subtree minus height of the right subtree. If this value ranges between the -1, 0 or 1, only if it ranges with these three values, then only it is known as your AVL tree. For every node, we need to calculate the balance factor. And if the balance factor remains in these three values, then only it is called as your AVL tree. If not, it is not balanced and it is not called as an AVL tree. So I will do one example based on. Then I'll show you one program related to this concept. Okay, now I just want to calculate the balance factor of 10. What is the left subtree? 0. What is the right subtree? How many nodes are there? 2 nodes. 2 nodes means you should not take like number of nodes, ma. One of the longest path you need to consider, and in that longest path you need to pick the count for the path. How many paths are there? Only one single path, that is 20 and 30. So how many nodes are there? 2. So the balance factor for the left subtree is 0. For the right subtree it is 2. 0 minus 2. What is the value? Minus 2. Is that balance factor ranges from the -1 to 1? No. So it is not an AVL tree. Now I need to convert this particular tree as an AVL tree. How can I convert it? Means by performing the rotations. What are those rotations? 4 types of rotations are there, ma. Left rotation, right rotation, left-right rotation, and right-right rotation, right-left rotation. Left rotations means LL rotation, RR rotation, LR and RL rotation. These are the 4 different types of rotations. For them, commonly we have given single rotation and double rotation. So please look at this concept clearly. So under the AVL tree, we have the definition like our binary search tree only. It follows the condition that left less than root less than right. But still it has to follow one more condition. That is the balance factor should range between the -1 to 1. What is meant by balance factor means height of the left subtree minus height of the right subtree. Okay. Right. So what are the rotations we are having means rotations. We are having two types of rotations. Single rotation and under single rotation we are having LL rotation and RR rotation. Under double rotation, we are having LR. That means we need to perform left, right, both at a time. Then RL rotation. These are the four different set rotations which we will follow in our ABL. Under LL rotation means it's just a U-turn to left. Under RR rotation means U-turn to right. Left LR rotation means first perform the RR. That means U-turn to left, then the LL rotation. How those occurs, I'll just give you each and every one example. First, I'll give you an example for the LL rotation. LL rotation means, suppose you have value 10. Your left child is some 5. Now please calculate the balance factor. First, before inserting 5, what is the balance factor of 10? Left is 0, right is 0. That means no left child, no right child. So the balance factor is 0. It is balanced, well and good. Now I am adding 5. So it will be a left child for the 10. Now please calculate the balance factor for 5 first. Please always come calculation from the bottom to top, not from the top to bottom. Okay? Right. So what is the balance factor for the 5? Does it have a left child? No. Does it have a right child? No. So the balance factor left, right, minus will be 0. So the balance factor of 5 is 0. Now getting back to the balance factor of 10. Left minus right. What is left? How many nodes are there? 1 node. What about right? Nothing. So 1 minus 0, 1. Now I just want to add the node 2 into the tree. It will become the left child for the 5. Isn't it or not? Yes. Now please calculate the balance factor of the 2 first. Balance factor of the 2 I need to calculate first. Right? So 2 balance factor means left, right are zeros. Well and good. Balance factor is 0. Now coming back to the balance factor of 5. Left we are having 1 node. What about right? Nothing. So 1 minus 0, it is 1. Now please look at the balance factor of 10. How many nodes are there in one of the possible path of your left subtree? 2 nodes. What about the right subtree? 0. So 2 minus 0. What is the balance factor? 2. Is it balanced now? Is it there in the range of your balance factor? Is it or it is violating it? Yes. Is it there in the balance factor range or it is violating? Yes, ma. Yes, am I not clear? Yes, ma. So here, by inserting the left node, left subtree insertion, the root node is getting affected. So we are going to perform LL rotation. LL rotation means what? Turn towards the right. One node ahead right you need to turn. So how we are going to turn that? Become 5 will become as a root node and 10 will become the right child of 5. 2 remains as it is. So how your tree will become now first? I should turn towards the right. So 5 occupied on the top. Towards its left, it remains with 2. With some space on the right side, it will be like 10. This is what LL rotation, just U-turn to the right. In the same way, if I want to explain the RR rotation, that means you are having the value like 30 and you have inserted the value 60 and still you have inserted the value 80. So right is skewed. Now to overcome this imbalance in it, I need to take U-turn towards the left. So my 60 will become the root. 60 left, your 30 will be moved down and 80 will be your right child. This is what RR rotation. The combination of these two will affect me the LL and RR rotation. The case I have to take it as left-right rotation. Left-right rotation means for left subtree, if the right node is getting added, your root balance factor will get changed. So that is what the combination of RL rotation. So I'll take one example. If I take the 45 as the root node, if I take 45 as the root node, and if I want to insert, 35, it will be a left child. Suppose if I want to insert 38, where it will become right child of your 35. Now, please look at here. For the left subtree, right node, if I am adding, the balance factor of the root node is getting defected. So what I need to perform? Left subtree, right node insertion is affecting the balance factor. So I need to perform LR rotation. LR rotation means first I need to do the RR rotation. RR rotation means what? You turn to left. So your tree will become 45 remains as it is. What is the rotation you are performing over here? RR first. RR rotation you are doing. So what it will be? RR rotation means you turn to left. 35 will be moved down and 38 will occupy its position. So your 35 will be moved over here. Now, did I finish the rotation completely? No, still I need to perform LL rotation. LL rotation means what, ma? You turn to right. So my 38 will become the root node and my 35 will be my left child and my right child is 45. This is what your LR rotation. That means performing the RR rotation followed with the LL rotation. Here is one example for it. Now please, coming back to the next rotation, that is RL rotation. If I take the example as, suppose I've taken the root node as 56 and I've inserted the next value as some 68. Now I just want to add the value 60. So it will affect the balance factor of the root 56. By what insertion it is getting affected? Right subtree, left node if I add it, it is getting affected my root value. So I need to perform now right subtree, left node. So RL rotation. In this scenario, first we need to perform the which rotation? Can anyone please tell me? First we need to perform the LL rotation. LL rotation means what? You turn to right. That means 60 will occupy the 68 position and 68 will be moved down first. So your 56 will remain as it is. Then you are having a right child, that is 60. And for that you had one more right child. Let me take this to the down. Sorry, ma. Wait a second. To the right child of it, it became. So So to the right child of it, it got became the 68. So this is what after performing the LL rotation. Now I need to perform the RR rotation. That is you turn to your left. That means after performing the RR rotation, which node is becoming the root node? 60. And what is your left child? 56. What is your right child? 68. This is what the complete scenario of constructing the aerial tree. Right? Are you comfortable with this concept?
Yes.
Did you understand the creation of binary search tree and aerial tree?
Yes.
Okay, ma. I'll show you the code related to it in the lab. Okay. The specialized tree. This is what about your binary tree and aerial tree. Yes, here is your program, where it has some inner functions in it, which will perform all that operations which are related to your trees. So I'm not showing this example. Let me show the clear one. Always remember the execution steps of your Java is Java C space file name dot Java extension. Once you got clear with all the errors and everything, you need to run it by using the command Java space your file name. Remember this, ma. Don't forget it. Okay. Here is your insert code, new code. Yes, I'll go with this binary search tree program. Please look at here. Just give me 2 minutes time. I'll conclude this code. Right. I already told you that in the tree, each node should contain a data part, a left node, and a right node. Yes. And if you take it as a constructor, node class under the class, if you take the constructor by the name node, this particular values will be filled. Default constructor, ma. Then the function display function means printing the value. Then insert is a function to add the root node. So while adding the root node, what is the condition we need to check? If the root is null, then new node. Whatever the value you have created, it will be added. That means if the tree is not created, for the first time it is there. If the tree is created, then what condition I need to check? If the inserting value less than the node value, that is your root node value, then please insert it to the left chain. Recursively, I am performing it. If it is greater, I am inserting it to the right chain. Here also it is a recursive call. Then please return the root node address. Find means search function, searching whether the required node is present in the tree or not. If the required node is less than the root means it will skip the right part. It will check only in the left subtree. And the process continues by using the recursive function call. If the tree root node is none means the tree is not created. Then traversing means just now I've discussed. We are having 3 different traversal methods, but either of the one is useful. But you need to learn all those 3. What is the principle we are having for the in order? Left, root, right. Pre-order, left, root, left, right. Post order, left, right, root. Remember these formulas. By that you can achieve your answers easily. Right. Here you go with the implementation of your main method, where we are supplying with some values which I want to insert into my binary tree. And I've taken the example of your fractional values. Usually we'll implement with the integer values, which is well known to you. Just for practice purpose, I've taken it in the float. Okay. Try to do it. Try to practice this program. Okay. Here is the output for it. Can I continue with the next specialized trees, mass? Play trees and B plus trees, B trees? Or shall I continue tomorrow? That means on 13th. Trees concept, are you comfortable with this?
Yes.
Okay. I'll continue it in the next class.
Okay.
Thank you, ma.
Thank you.